All right. A few quick announcements. If you still need a hard copy of the syllabus, I have a few more copies up here, but be advised those, apparently the printer ran out of paper and didn't tell me last time, which is why we were short a few. So these are the copies of the syllabus that were printed out last time, which don't have the typo on the midterms corrected. So the most up-to-date and correct version is still to be found on Icon. So a few other items. I've got some emails about textbooks, and I'll go ahead and say the same thing here I've been saying to those people. You can get any edition of the textbook you want. The ISBN that was listed for the course is this guy, a soft cover version. Ordinarily you can't buy this, but I negotiated a deal with Wiley to get them bound and get you guys about 50 or 60 bucks off the price that they would ordinarily charge. So if you use the ISBN that's on the syllabus and on the course listing, you'll get one of those. But you can go anywhere back to, I think there are still 5th editions floating around, and that's personally what I use when I'm preparing lecture notes. I'll be posting all the homeworks online, so any edition will do fine. Next week, I mentioned this last time, I'm going to be out the whole week because I got experiments to run. The lectures are going to be covered by either, well, by Professor Mantia and or Professor Bill Eichinger. I'll let you know when we approach those dates. But if Prof. Eichinger covers, they'll be here. If Prof. Mantia covers, then I have a room reserved over at Phillips Hall where both sections are going to meet. So it'll be just a really large class for that week. TAs, we're still working out some of the details. We have 2 sets of TAs. Those that are going to be available for homework help are Victor and Michael. I'm meeting with them tomorrow morning, and we're going to set up their office hours, so I'll get the information to you as soon as possible. The TAs to help you out with labs are going to be Randall and Mehdi. Their standing office hours are listed here, so one after another on Wednesdays from 12:30 to 2:30 total. But in addition, there are going to be set lab work times that you'll be meeting with those TAs. So that's what this here shows. I'm going to post this up on Icon after this lecture, but the lab schedule is shown here. So we're in week 1, no labs. Okay. Next week, you're not actually going to be doing labs. It's going to be sort of an introductory session in a conference room with the TA where they're going to do an introduction on what are experiments, what kinds of sensors do you use, how do you do uncertainty analysis. This is to set you up for the stuff you'll be doing in Lab 1. Each lab, of which there are 4 total, is sort of designed as a 3-week module. During week 1, you'll do the lab. During week 2, you're going to meet with the TA in a conference room that's been reserved as sort of a workshop on data reduction and data analysis, and they'll help you with questions on the spot about how to process the data. So the idea is bring your laptop, bring your data, work on the actual number crunching there. So you can ask questions as you go. And then you'll have another week after that during which to write up the lab report. These are generally short, 2 to 3 pages. The idea is I don't want you spending a lot of time writing. I know what you did, and I'll get you more details on those as we approach the start of Lab 1. So, thing to remember right now is next week, show up to your assigned lab time, okay? And that's going to be in room 3258 over in Siemens Center. And you're going to spend, 45 minutes to an hour, so about half of that allotted lab time, going through some of the preliminaries with the TA. So, all right, today we're talking about, well, really 2 topics, but 1 subtopic here, okay? The first is going to be the ideal gas law, which is something that you guys have probably seen before. And the second is going to be viscosity, which you've probably heard mentioned, and you might have some idea of what it is. For example, it's the difference between, let me go ahead and start that over. It's what differentiates the behavior of water on the left from silicone oil on the right. They both have similar densities, but very different viscosities. And so it's that viscosity that we will understand by the end of this lecture to cause this difference in the way they slosh around and the way they pour. Another way to refer to viscosity is sort of a notion of fluid stickiness. Okay? And then sort of a sub-bullet under viscosity, we're going to discuss the 2 main classes of fluids, those being Newtonian and non-Newtonian. So let's go ahead and move to the notebook. So, the questions we want to answer by, oh good, let's make that show up again. There we go. So the questions we want to answer by the end of today, or the goal by the end of the lecture, we want to be able to relate fluid density, which we discussed last time, pressure, and temperature using the ideal gas law. We want to define fluid viscosity, differentiate Newtonian and non-Newtonian fluids. And then finally, is where the numbers actually come in. We want to be able to relate velocity gradients in a fluid to shear stress. And it's the definition of fluid viscosity and this idea of a Newtonian fluid that will allow us to do that. All right, so recall that fluids encompass 2 classes, right? Gases and liquids. And they differ based on what property? Like why are liquids and gases different? Anyone? Compressibility, right? Gases you can squish, liquids you can't. So liquids are what we call incompressible, and gases are highly compressible. So this creates a problem for us as scientists, because if we're working with liquids, right, we can say, all right, it's incompressible, the volume doesn't change, right? It's easy. If we know the volume at one time, we know it at another time. It's going to be the same. But with gases, because they're highly compressible, they're sort of the springy medium, we need some theory to describe how that volume changes, or how they compress under the influence of pressures and temperatures. And that's where the ideal gas law comes in. So this should be familiar to you from thermo and or chemistry. The ideal gas law is written in several ways. In this course, we'll use this expression. The density is equal to the pressure over the gas constant times the temperature. Or, the pressure is equal to the density times ideal gas constant, or the gas constant times temperature. And in these expressions, right, rho is defined as density and has dimensions of mass, length, -3, right? Think about typical units, kilograms per meter cubed. T is the temperature, which needs to be an absolute temperature, meaning Kelvin or Rankine. This has dimensions of theta, which stands for temperature. P is pressure. Again, this needs to be absolute. That means measured with respect to 0, a complete vacuum, as opposed to measured with respect to the air around us. Use a tire pressure gauge, right, to measure the air pressure in your tires. It reads 40 psi. The absolute pressure in that case is going to be 40 psi plus the 14.7 psi that is atmospheric, because it's a balance between the two pressures, right? It's giving you the difference. So for the ideal gas law, we need to make sure that we are adding in whatever the ambient pressure is if we're using a pressure gauge. We'll talk more about this in the next chapter. And R is, of course, the gas constant. This pressure has dimensions of mass, length -1, time to the -2. And if we went ahead and went through the kind of dimensional analysis we did in the last lecture, we'd find that R has units or dimensions of length squared, temperature to the -2, time to the -2, temperature to the -1. So the ideal gas law is all over engineering. We use it a lot in aerospace and a lot in chemical engineering, thermodynamic processes, etc. And you probably have a fairly intuitive understanding of how it works. For example, if we were to say, let's hold the temperature constant, okay, well, then what that says is that the pressure and the density are going to be proportional to one another, right? Or if we say that, so let's see, for constant temperature, rho, which is equal to the mass over the volume, okay, is going to be proportional to the pressure. And this is something we know as Boyle's law. In other words, it's saying that if we were to plot out the volume of a gas against the pressure of a gas, they would have an inverse relationship. If it was a constant temperature. And as I said, this is known as Boyle's law. On the other hand, if we were to say, let's hold the pressure constant, we were to plot, in this case, the temperature against the volume of a group of gas molecules, we would find that they vary linearly to one another. So what this says then is that T, right, is equal to P over rho R, which is equal to P V over R M, where M is mass, V is volume, and this guy's constant, this guy's constant, and of course, because of conservation of mass, the mass is constant. So this says that the temperature and the volume have to be proportional to one another. And this one we call Charles' law. So these are just two variations on the ideal gas law that you've probably encountered before. It's been a long time since I've taken chemistry, so I don't remember what's in the curriculum. But these are based on the more generalized ideal gas law. So let's do a quick example. So this is problem 147 from the book. The idea is we've got a closed tank. Okay, and this tank is full of an unknown gas. However, we know that the mass of the contents of the tank is equal to 0.3 pounds mass. We know that the volume of the tank is 2 cubic feet. And we've got a pressure gauge, okay, on the side here that's reading 12 psi. So the question, now somebody says, all right, here's this information about this tank and the gas inside of it. Is the gas oxygen or is it helium? Find oxygen or helium. So we've got all the information we really need here, right? We know the pressure, we know the mass, and we know the volume. And we have a temperature probe. That's what I'm missing here. We've also got a temperature probe that says the temperature is 80 degrees Fahrenheit. Okay. So we've got T equal to P volume over R mass. Okay. We know the temperature, we know the volume, we know the mass, we know the pressure. So because we know all those things, right, it's easy to find R. And R is different for helium than it is for oxygen, so that should be our clue. The real trip-ups here is that we need to remember that we're using absolute units, right? Degrees Fahrenheit, not absolute. The reading from this pressure gauge at 12 psi, not with respect to 0. It's with respect to atmosphere. And so we need to go through and we need to translate all of our measurements into absolute units, plug them in, find R. So go ahead and see if you guys can get a head start on the absolute temperature and absolute pressure. R, solving for R is going to be then. What do we got for an absolute pressure? Anyone want to volunteer? Well, what's atmospheric pressure? What's 1 atmosphere? 14.7. Okay. So if that pressure is saying the pressure in the tank is 12 psi greater than that, then just add the 2. So we're talking about 26.7 psi. Which we'll see in a second, right? That everything else we have feet. We have feet for the volume. We've got we're gonna have our temperature in Rankine, and so it works out better if we put this into pounds per square foot, which means multiplying it by 144. So this actually, if we just multiply that by 144, we end up with 3844.8 pounds force per square foot. So it's a -2. Okay. Temperature. It's I know for me it's been a while since I've done absolute units or absolute temperature units from Fahrenheit. Who remembers the translation from Rankine to Fahrenheit? Kelvin's 273. Rankine is 460. So in this case, if 0 Fahrenheit is 460 degrees Rankine, degrees Fahrenheit plus 460 degrees gives us 540 degrees Rankine. And then the density, right? We could use volume and mass, but since we just talked about this last lecture, let's make sure we're fresh and remember how to do the density in a way that's consistent. We know we've got 0.3 pounds mass in a volume of 2 cubic feet, right? So it should just be as simple as dividing that mass by volume. But remember, we're in customary units, and people that invented those wanted us to have headaches, so we need to translate it into slugs. So it's 0.3, right, pounds mass divided by cubic feet times 32.2. Right, this is conversion from slugs to pounds mass. And so this is going to work out to 4.66 times 10 to the -3rd slugs per cubic foot, which would be 0.15 pounds mass per cubic foot. So, quick little question here. We have density, right? Well, clearly, at atmospheric pressure, helium and oxygen have different densities, right? It's why helium floats. So could we just take that density number and go look it up in the table of properties and tell which gas it is? I guess hands up if that seems like a reasonable way to do it. Hands up if not. Got a couple of curious hands. Anyone want to suggest a reason why? Because those tables in the back of your book generally don't give you densities other than at atmospheric pressure, right? It is pressurized. It's been compressed, the density increases. That's what we just said. Well, it's one of the things we said up here, right? That pressure and volume are inversely proportional, so pressure and density are proportional. So that is one of the reasons that we need to go through this process of finding R, because R is a constant. R doesn't depend on temperature, it doesn't depend on density, it doesn't depend on the pressure. So if we go ahead and plug these all in, right, we say that R then is equal to this 3844.8 pounds, little wobbly lectern, pounds force per foot squared divided by 540 degrees Rankine times 4.66 times 10 to the -3rd slugs per foot cubed. What we'll get is a value of 1,528 foot-pounds force per slug degrees Rankine. Now, if we were to go to the back of our book, or I guess the front of our book, depending on which book you've got, and look up the gas constants for helium and oxygen, what we would find is helium R is equal to about 12,420 pounds force feet per slug Rankine, and oxygen R is equal to about 1554, the same units. So clearly, if we compare these, it's obviously not good. We're off by a whole order of magnitude there. And so we could say with reasonable accuracy that this is probably close to pure oxygen in the tank. Okay. Yes?
Why did we get rid of the volume?
Why did we get rid of it? Well, we didn't get rid of it. We just divided it. Instead of plugging in the volume right here, we took the volume and the mass and turned it into density and put it in there. So we could do it either way. Okay. All right. So I'd love to keep talking about ideal gas, but our time together is short. So we're going to jump onto the topic of viscosity. And I'll give you guys a few more seconds with that to finish copying if you need. So like I said before, viscosity, right, is this notion of fluid stickiness. Okay, it's what dictates the numbers on the motor oil you put in your car. It's what dictates the reason that molasses is harder to pour than rubbing alcohol, right? And it's one of the things that dictates how hard it is to pump things through pipes or to pump blood through blood vessels, right? So quickly, I want you to recall our definition of a fluid, right? Not gas versus liquid, but just any fluid. And that was a substance that deforms continuously under an applied shearing stress. So I want to formalize this really quickly, right? Because probably from previous, if you've taken def bods or the continuum mechanics class, you've seen the idea of shear stress and deformation. But it pays in this class to make sure we're all on the same page. So I want you to consider a small little area. Okay, this little blob here is a small area we'll call delta A. Now the definition of stress is force divided by an area. Now if we apply a small little force directly downward on this area, this is what we would call a normal stress, because it is being applied in the same direction as the normal to this surface, right? It's perpendicular. So a normal stress, and this is something that we more frequently refer to as pressure. However, if we have a small force that is being applied tangential to this surface, that is, it's right in a direction that would cause friction as opposed to just pushing or pulling, then this is what we would refer to as a shearing stress. So the idea here is, said before, I want you to visualize, if we were to take a solid object, okay, this is a very poor demonstrator of a solid, but if we were to take a solid object and we were to apply a shearing force to it, right? If I were to push with one hand and pull with the other, the idea is that there's being a force being applied over a surface area, so it's creating a shearing stress, right? But notice if I apply a static force the eraser, you can't really see it very well, but it deforms a little bit, right? It takes on an angular deformation. So that's a hallmark of a solid, is that, oops, change this to a black. So with solids, I've said this before, that if you take an object and you apply a shearing stress to it, right, which we will refer to as tau, is the symbol for shearing stress, which is equal to F over the surface area that's being applied, then what will happen is that surface will, or that object will deform into this sort of parallelogram. And this angle, right, of deformation is what we would call beta, or the shearing strain. So with solids, the classic law, Hooke's law, says that shearing stress is proportional to shearing strain. That is, if I double the force that's being applied to the same area, then the shearing stress will also double, and so will this deformation. Okay. Classic continuum mechanics for solids. Fluids, it's a different story. Fluids, if I have, let's say I've got two parallel plates. Okay, the plate on the bottom is glued down to the floor, and the plate on top is free to move. And between these plates, I have a fluid. Now, if I apply a force to this plate, F, which is our applied force, and the top area, the plate has an area of A, then once again, I'm creating a shear stress between the plate and the fluid of tau, which is equal to F over A. Okay. Unlike the solid, though, this isn't simply going to deform a little bit and then stop at a static equilibrium. With a fluid, okay, the top plate is going to begin sliding continuously at some constant volume, or some constant velocity. And so that constant velocity of the top plate is going to create a velocity gradient in the liquid. So the fluid is going to stick to the bottom plate, have zero velocity. At the top plate, it's going to match the velocity of that top plate, which we'll call U. As a result of this, because the top plate's moving at U, the bottom plate's not moving, and the fluid is moving between it, if we were to set up a coordinate system here and say that we measure y upward from the bottom plate, then the velocity of the fluid itself would be a function of y, which would be velocity of the top plate times y divided by b, where b is the distance between the plates. Okay, so it's just a linear variation from 0 up to u. At the same time, right, because it's deforming continuously, if we recall how we defined the shearing strain up here as beta, we don't have a single value of beta. What's happening is that beta starts at 0 and it grows continuously. And because the top plate is moving at a constant rate, beta is increasing at a constant rate. And so rather than having beta, we're going to say that, define this d beta dt is the shearing strain rate. And this I did say during the last lecture, right? Unlike a solid, a fluid, instead of being governed by Hooke's law, has this law that says the shearing strain rate is proportional to the shear stress. So as with a solid, doubling the force that's creating the shear will double the strain deformation. In this case, doubling the force will double the velocity which with the top plate slides, and will double the the rate at which that angular deformation in the fluid increases. Okay. A couple more things here. So we can write that d beta dt is equal to, I'm skipping some of the derivations here, can be shown to be equal to the velocity gradient in the fluid. So if we look at the velocity of the fluid u, y, right? If we were to take the derivative with respect to y, we get what? U over b. Okay. So we could say that del beta del t, here the partial derivative of the strain rate with respect to time, is equal to u over b in this particular case. Now here's where this idea of viscosity and Newtonian fluids comes in. For fluids that we call Newtonian, and I did just give you a preview of this definition. We know that the shearing strain, the shear stress is proportional to the shearing strain rate. Stress proportional to strain rate. And because we've got this definition up here, we can go ahead and say, therefore, the shear stress is proportional to the velocity gradient in a fluid. Now, by going out and doing a bunch of experiments, okay, on different types of fluids, we have, when I say we, I mean that the scientific community has determined that there's a constant of proportionality that is particular to a fluid, and this is what we call the viscosity. So we found then that tau is equal to this variable mu times du dy, where this mu is what we refer to as the viscosity of the fluid. So to recap, a Newtonian fluid is one for which this is true, right? That the velocity gradient is proportional to the shearing stress. In a second, I'll talk about non-Newtonian fluids where that is not true. Non-Newtonian fluids are not something we cover in this class, though, so I just want you to know what they are. They're a lot more complicated to deal with. This is going to be our bread and butter for the class. And this is one of the main, that you want to, if you remember nothing else from this class, remember this equation. Right? This is the fundamental governing or constitutive law for the way fluids move under stresses. Yeah?
Is that du or du?
That is, sorry, that's du.
Are they all du or just that one?
dy. These are u's. Alright, so for viscosity, we've got this variable we just defined, mu, which I'll try to make sure I keep distinct from my u's here. This mu, which we would call the dynamic viscosity. Sometimes you'll see it in your books, and you'll see it sometimes in this course. There's also what we'll see, this thing called kinematic viscosity, and this one I need to be careful. It doesn't look like a V. This is a nu symbol. And this is what's known as the kinematic viscosity, and this is simply defined as mu divided by the density of the fluid. All right. So the idea is that these are not two different properties. If you know the density, then you can flip back and forth between kinematic or dynamic viscosity. But they can be more convenient to use one or the other in certain instances, and we'll see some of those to come. Just for now, remember those definitions here, dynamic versus kinematic. All right, so as I said, this holds for most actually for all Newtonian fluids. And Newtonian fluids, luckily for us, makes up most fluids that we're going to deal with. So Newtonian fluids, right, are these ones where we have the rate of shearing strain and we have the shearing stress. There's a linear relationship between them. But that constant, right, that viscosity changes depending on what fluid we're talking about. So for example, air, not very viscous. That's why if you're waving your hand through the air, you don't feel this big frictional pull that's resisting your motion. Whereas if you were trying to wave your hand through a tank of crude oil, right, there would be a lot more resistance to your motion as a result of that viscosity. Non-Newtonian fluids, on the other hand, shown on the right, as I said, are the ones where we don't have this nice proportionality between shearing strain and shearing stress. There are three types of non-Newtonian fluids. There are what we call shear thickening fluids, which, as the name implies, means that as you shear it, right, as the rate of shearing strain increases, which would mean if you have those plates sliding past one another, you start to slide it faster and faster and faster, then the resistance to that motion increases drastically. In other words, it gets harder to shear the faster you shear. Shear thinning fluids, on the other hand, get easier to shear as you shear them. And then Bingham plastics are ones that behave like a solid up to a certain shearing stress. Okay, so there's no shearing strain rate. They'll stay in a static equilibrium until you hit some threshold, and then they'll begin to act like a fluid. So examples of shear thickening fluid would be something like a mixture of cornstarch and water, okay, where it may behave as a fluid when it's not being sheared very quickly. So if you take a mixture of cornstarch and water, put it on a table, it'll spread out in a very fluidic manner. But if you go and try to subject it to really rapid shearing strains, as by pushing it around with a spoon, it starts to thicken up. Okay. A shear thinning fluid would be something like house paint, okay, where as you brush on paint, right, the idea is it should spread smoothly and easily as you brush it, but then once you stop brushing it, you're no longer shearing it. You want it to stay put, more or less. Okay, you want it to get harder to shear as you, proportionally harder to move as you reduce the rate of shearing. So if you think about house paint, often as you're brushing, it's actually harder to push the brush, or seems harder at slow speeds than if you brush faster. And something like a Bingham plastic, an example would be like toothpaste or mayonnaise. Something that has more or less, it can be kind of gelatinous, but it behaves like a solid until you push or pull on it or shear it to a certain threshold, and then it'll start to behave in a fluidic manner. I have more examples of these that we'll come back to if we have time, but for the moment I want to make sure we hit on an example of how we would actually calculate the shear stress in a fluid. Okay. So this is example 1.5 from the book. So the idea here is we would have two plates. Okay, in this case, both of these plates are fixed. All right, and then between these plates, we will have a fluid. Now these plates are located or arranged with a distance between them of 2h. That is, so from the center line between these plates to either of the walls would be a distance of h. And we're going to go ahead and put our coordinate system right here on the center line. So here's x, here's y. Now we'll show this later, okay, how we actually get to this result. This is not till chapter 7, I think. If we were to push fluid through this pipe, we're going to get a velocity distribution that looks like this. Okay, it's going to be parabolic in shape. So here's the velocity of the fluid flowing between these two plates, and it has functional relationship that looks like this. Uy is equal to 3u divided by 2 and 1 minus y over h squared, where u is, we don't know what this is in terms of numbers, but this is defined as the mean velocity through the pipe. So the question is, can we find the shear stress tau at 2 points? On the bottom wall, and at the center line between the two plates. And that should be an A there. All right, so we've got our definition of how to find shear stress, right? We're not going to worry about the numbers here in terms of what the viscosity is and what that big U is. We want to just find this symbolically because we could plug in values later if we look them up in a book. So for part A here, we would say, okay, we know that tau is equal to viscosity times derivative of u with respect to y, and we would be evaluating this at y equals what for the bottom wall? Negative h, right? Because y is measured from the center line of the pipe, or center line between the two walls. So go ahead and calculate the derivative du dy, or the derivative du dy, while I write out how we would do this for the part. We're going to need that derivative for the second part as well. So dust off your calculus books. Okay, who's got a derivative for the velocity? That is an expression for the velocity gradient. Any takers?
3 halves big U times minus 2y over h.
3 halves.
I guess
Yeah.
you could cancel out the 2's. But
Right, the 2's would go away. So it would end up being 3 u y over h. The h there would end up being squared, yes? No. No, it wouldn't. Yes, it would. Yes, it would. Okay. And then we'd end up with a negative sign out in front. Okay. Because of the negative sign here. All right, so finding the shear stress at those two different locations is just as simple as plugging in y equals negative h and y equals 0 for these two, or into that expression over there. So at the bottom wall, where y is equal to negative h, okay, we would plug in a negative h here. One of those powers of h would cancel out, and we would end up with tau is equal to mu times 3 u over h. Okay. For part B, if we plug in 0, it's pretty clear that, right, for y equals 0, the rest of the expression is also going to be 0. Mu times 0, okay, which equals 0. So we might ask ourselves, like, how does that occur, right? We've sort of implied that fluid motion is associated with shear stress. Okay. So if this fluid is flowing, how is it that we get a zero shear stress at the center of the pipe? A nice way to sort of visually look at this is we said, right, that the shear stress is proportional to the derivative of the velocity with respect to y. So if you come up with a case and you see a velocity gradient, that's actually been plotted out, and you were to go ahead and draw a line that is, tangent to that velocity gradient at different points, then, for example, at the center line of the pipe, right, that tangent line is straight up and down. This tells us, right, that if we were to kind of turn our head sideways, it's a zero slope. So that because the velocity gradient at this point is zero, and so is the shear stress, okay, only along the center plane between the two walls. Whereas at the bottom wall here, if we were to draw a gradient line, it has a very high slope, which suggests that's going to be the point where the shear stress is non-zero. Similarly, we could say, well, where is that gradient highest? For a parabola, right, the slope is greatest furthest from the origin of that parabola, so near the walls, the shear stress is the greatest. So some little qualitative tools that you can use to sort of visualize where shear stress is occurring. All right, so on Friday, we'll move on to finish Chapter 1. I posted homework 2, and if you haven't seen it yet, right, lecture recordings, the videos can be found on Icon. If you go to the UI capture recordings, those should start showing up after each day's lectures. Yes.
4 minutes later,